Hello everybody, we will be talking today about magnetic fields produced by currents. You probably have noticed, or when you were in high school or even before, you may have done this experiment in a science lab or something like that. You have a battery and there is a wire wrapped around a nail, and you pass a current through the wire from the battery, and then you bring the whole system near the magnetic material or iron or whatever, and the new kind of like nail with the wire wrapped around it with the current inside acts as a magnet. It attracts iron. So this actually was discovered almost about 100 years ago. There was a Danish scientist, his name is Ørsted, and he was actually working with currents. He was not trying to find anything about magnetic field, but he had left accidentally a compass next to a wire. So when he passed a current into the wire, the compass needle changed its direction. And we know that compass needles change its direction towards the Earth magnetic field. So why did it change its direction when a current passed through a wire? Then he discovered that there was something else going on, which is when a current goes through a wire, a magnetic field is created. Okay, so there are several wires. There are wires that are straight, there are wires that come into circles, there are wires that come into like a coil or a solenoid. So we have, for each wire, we have a different type of a magnetic field. Okay, but to start off, we are going to look at first at a wire that is straight. So let's say we have a straight wire like this one, and in this wire there's a current I that is going up like this. So the current I that's going up like this. If there is a wire like that with a current going up, then a magnetic field is created around this wire, and this magnetic field takes the shape of concentric circles. So it's actually infinite number of concentric circles, and it's all over the place. It's like a total cylinder surrounding what? The wire. Now, where is the direction of this? Remember that the wire has the current that is going up like this. Okay, so the direction of the magnetic field can be found by what it's called the second right-hand rule. We know the first right-hand rule is to use to find the magnetic field force on a moving charge within the vicinity of a magnetic field. But now we are going to talk about finding the magnetic field direction created by a straight long wire. And for that, what you do is simply, let's imagine this is the current, and the current is pointing up where the direction of the pen is. Okay, so the current is like this in the wire. So you grab on the wire such that your thumb is pointing to the direction of the current. You see that? Now look at my hand. My hand here is going inside the page on the right, and the fingers are going outside the page, so it loops around. So if I do this here, if I grab on my hand such that my thumb is here and my four fingers grow like this, because my four fingers are gonna wrap around. Okay, so this is the thumb and this is my four fingers. So on the right side of the wire, the magnetic field is going in, and because my four fingers are gonna come peeking out from the other side, it's going to be coming out like this. Okay, so around the wire, to the right it's going in, and to the left it's coming out. So it's like a circle that goes around the wire in to the right and coming out from the left. And this is called the second right hand rule. Okay, so let's try this again. So I have a wire, so I'm gonna have a wire like this, and the current is going like that. Okay, again, so this is the current. Okay, I grab on it so that what? My thumb is pointing to the direction of the magnetic field, and look, see, so to the right here on this side, it's going in and my 4 fingers on the other side is going out. So again, this here happens like this. Okay, it is not as hard as the first right hand rule. It's just like, you know, you just have to practice a little bit more. So let's have another current here. So I'm gonna make up another current like this. How about this current? What do you think? Okay, let's do that. You grab on it. So this is the current going down where the pen is, and I'm gonna grab on it so that my thumb is pointing this. So look, my 4 fingers above the current are going inside, and they're wrapping around like this. So above the current here are going inside and coming out here. So this is a concentric circle that's going like this, coming out and going inside like that, and so forth. How about this? What if there's a current that looks like this? So that's I. Okay, so that's I. It seems that I is going within to the screen. So you put your thumb on the screen, right? You put your thumb on the screen like this, because your thumb should be pointing towards where the current. So I'm gonna put my thumb on the screen here, like this, okay? And if I do that, then it seems that the magnetic field direction is like that. And I hope that will help and you get the idea. Okay, all right, and that's it for the direction. Now for the value of the magnetic field. Okay, let's look at that. Let's look at that together. Let's say I want to find the magnetic field here, okay, and this magnetic field here at a distance r. I'm going to call the distance r. Okay, if I want to find it at another distance, the magnetic field here, I'm going to call this R2. If I did this experiment in the lab, I will find out that the magnetic field drops when I go further away from the wire. And that makes sense, because the further away from the wire, the weaker the magnetic field. If you are close to the wire where the current is, then the magnetic field will be much stronger. Okay, if that's a fair statement. So how much does it drop? It was found out by experiment. It drops down just by the same ratio. So if you double the distance, the magnetic field goes down by half. Okay, so they found out that the magnetic field is inversely proportional to the distance r from the wire. Okay, what else is there? They compared it with the current. So the current, when they said, okay, if the current is big, what happens with the magnetic field for the same distance? So let's look at this distance r. Okay, and we doubled the current. We measured the magnetic field before we doubled the current, and we measured the magnetic field after we doubled the current. We found that the magnetic field was twice as much. So it is directly proportional, and not only that, it is linearly directly proportional, which means that if you double the current, it doubles the magnetic field. If you triple the current, it triples the magnetic field. So it was found that B is directly proportional to I. There is no square, there's no square root, there's no exponential. It's the simplest relationship we're looking for, which is really nice. Good. So now is there anything else we need to look at? They found out that these are the only two main variables, and they put these together here. So they said, okay, B is directly proportional to the current divided by R, and when we change the proportionality sign into an equal sign, B was equal to a constant times I over R. Now, finding the constant was not the simplest of tasks. So they did an experiment, and many experiments, okay, like drawing graphs and finding like numbers and all these things, and then they found out after that this constant, I'm going to write it down here, is called mu naught over 2 pi. That's the constant that they were looking for. All right. Now IR comes as it is, so I'm going to multiply it by I divided by R. Now this mu naught is called the permeability of free space. So I'm going to write it down, permeability of free space. It's called the permeability of free space, okay? And mu 0 as a value is equal to 4 pi times 10 to minus 7 Tesla meter per amp. Okay, you don't have to memorize this number, it will be given to you. Okay, now what does the permeability means? Okay, this is kind of like a new concept. Do you guys remember when we talked about the electric field between the two charges, like Q1, Q2, or let's say the electric force, not the electric field, the distance between them is R, and we found that the force is equal to a constant which we knew as 1 over 4 pi epsilon 0 Q1 Q2 divided by the distance squared. Okay, what did we call this epsilon 0? We called it the permittivity of free space. Okay, which is like something we use. For example, if these two charges were set in a medium other than free space, epsilon 0 will not be epsilon 0 anymore. It will be called epsilon, depending on that space, depending on that medium. It could be water, it could be plastic, it could be rubber, whatever that is. So epsilon 0 represents the medium basically between two charges, but for the electric force. It influences the force between these two electric charges. Now mu 0 is the medium for the magnetic field, and it influences how much magnetic field is transferred through space or through the medium. That's what mu 0 is. Look, mu 0 here is on the top numerator, but epsilon 0 is in the denominator. So it seems that they are opposite to each other. If this, for example, was present in a medium other than free space, it seems that the magnetic field will be enhanced. But if the two charges were present with a medium other than the free space, it seems that the force will go down. So they are opposite to each other, which is an amazing thing. That's one of the major differences between electricity here and magnetism. All right, we will talk about this later. Thank you very much.